Hello, in this video we will solve this problem of electrical network wherein you have to find the current through this 1 ohm resistance. This is a given electrical network. We would solve this by 3 methods. Method 1 is using Kirchhoff's rules. Method 2 is employing the idea of combination of cells in parallel. Method 3 is using what is known as superposition theorem. So first method is using Kirchhoff's rules. So we see the introduction to Kirchhoff's rules. How to apply Kirchhoff's rules, first we will see, then go to the problem. Kirchhoff's laws of electrical network, there are 2 in number. First law is called Kirchhoff's current law, KCL, or junction rule. It states that the algebraic sum of the currents passing through a junction is 0. Algebraic sum of the currents passing through a junction is 0. So you should notice this, algebraic sum. That means certain currents you will take positive, certain currents you will take negative. So the currents going towards the junction taken positive, currents leaving the junction taken negative. If you want, you can even take the other way around. But generally, currents going towards the junction take positive, the currents leaving the junction take negative. Then find algebraic sum equal to 0. That is first law. First law is based on law of conservation of charge. See here, this is the part of an electrical network. And I3 minus I3 is equal to 0. See, this is the junction. This J, that indicates that this is the junction. I1 goes towards the junction. I2 also goes towards the junction. I3 is leaving the junction. See the arrows. So I1 positive, I2 positive, I3 negative. So I1 plus I2 minus I3 is 0. This is the statement in accordance with the first law. That means KCL or junction rule. You have got another law known as Kirchhoff's voltage law, written as KVL, or loop rule. The second law is applied to a loop. Okay, loop means the complete path, circuit, closed circuit. So that is the loop. For example, here you can start from here, go to here, 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 and come back. This is a loop. Okay. So we now see the statement of KVL, algebraic sum of changes of potential. Here also algebraic sum. The changes of potential means it can be potential difference across the resistance, or it can be the EMF values of the batteries and things like that. So algebraic sum of changes of potential around a closed path or closed circuit is 0. Here also we are using algebraic sum. That means certain voltage is positive, certain voltage is negative. So we give a sign convention for this. Which voltage you should take positive, which voltage you should take negative, we will give sign convention. For applying the sign convention, you will have to trace the loop. That means you will start from one corner, go around the loop, come back to the same corner. This is called tracing. Okay, that is called tracing the loop. Then when you trace the loop, you will be crossing the resistance. And the way of tracing and the direction of current is same, means the potential drop across that resistance can be taken negative. So I will just anyhow give this here, convention. If the direction of current through a resistor is same as direction of tracing, then the IR term means the PD, I into R, is negative. While tracing a loop, if one has to go from negative to positive of a cell within the cell, then the EMF is taken as positive. This is the convention. If you want to change the convention, you can change it, but change it for the entire statement. Meaning this you can take positive, this you can take negative. Okay. See, if you want to change the convention, you can change it throughout. This negative may come as positive. This positive may come as negative. Okay, this is the convention. This is the usual thing which is followed, but if you feel like changing it, Change here also and change here also. Now I will give an example for the application of KVL. Circuit is this. So A, B, C, D, A you can take as a loop or a closed path, closed circuit. You can apply KVL. You have to trace the loop. Let's say you start from A, go to B, go to C, go to D, come back to A. You are tracing in the anti-clockwise direction as faced by you. So this is how you trace it. So as you go from A to B, then from B to C, A to B nothing happens. From B to A, B to C when you go, you are crossing the battery. So EMF you are going from positive to negative. So this EMF you should take negative according to the convention mentioned. Then here the direction of the current is same as, opposite to the direction of tracing. So I to R2 positive. Then you continue tracing. Here you are going along the direction. You are tracing along the direction of current. So minus I1 R1. Here you are going from negative to positive within the cell. You take the EMF positive. So apply loop rule to A, B, C, D, A. Okay. So either you can write it in this manner or you can write in this manner. Both are same only. So this is how we will apply Kirchhoff's rule to an electrical network, both KCL and KVL. Okay. Now we will see how to do this problem using, this is method 1, using Kirchhoff's rules. You are giving this network, you are supposed to find the current through the resistance 1 ohm. Is it clear? So you label the commas E, F, then allot the directions of the current in your own way. I1, I2. So unknowns are only two, I1 and I2. You get two equations. By applying the KVL to each loop, left side loop and the right side loop, you will get one equation. Solve the equation for I1 and I2. Then find I2 minus I1, you will get the current. We are not sure whether the current will go from F to E or E to F. You allot it, later on you can give the interpretation accordingly. Okay, so applying the KVL, D, A, E, F, D, this loop, the first loop, we apply KVL. We have already learned how to apply tracing in the anti-clockwise direction. See, 3I1, the current comes, you are also tracing in the same direction. So 3I1 minus 1 into I2 minus I1 minus 6 is equal to 0. That has been taken to the right side. Okay. So simplify this. 3I1 minus of minus I1, so 4I1 minus I2, this 6 is coming as it is. Now apply it to the second loop, right side loop. This is also anti-clockwise. Okay. So I2 minus I1 here. I2 minus I1 into 1. Continue tracing. 3 into I2 because this current only will flow here. So 3I2. Then when you go or when you cross the cell, you go from negative to positive the cell. So minus 9 equal to 0. That minus 9 has been taken to the right side. So I2, 3I2, sorry, one more I2 is there. 3I2, 5I2, 1I2. 6I2 minus I1. Okay. 6I2 minus I1. Only thing I have written order the other way around. So 6I2 minus I1 is 9. Okay. Now here you have got 4i1, here you have got minus i1, so multiplying by 4 you will get minus 4i1, 24i2, 36, multiplying the whole of this equation by 4. Now there is one more equation we have already seen, that is 4i1 minus i2 is 6, minus 4i1 plus 24i2 is equal to 36. So you can solve. I write that equation here. So minus 4i1 plus 4i1. So when you add these two equations, i1 will get eliminated. Add. So 23i2 equal to 42. So i2 is equal to 42 by 23. So we found i2. Now we have to find i1. You can apply or you can substitute i2 in any one of the earlier equations. Okay. I apply here. We found i2. We want i1. So i1 is equal to 6i2 minus 9. For i2 you put 42 by 23. Simplify. You will get i1 as 45 by 23. Already you found i2 42 by 23. But we want to find current through this 1 ohm resistance. So 45 by 23, 42 by 23, i2 minus i1 will give you current through the 1 ohm resistance. Is equal to i2 minus i1, 42 by 23 minus 45 by 23. Simplify. Minus 3 by 23, which is minus 0.13 ampere if you want to have it in decimal notation. This negative symbol indicates that the actual current flows from the in the opposite direction to which you indicated. You indicated I2 minus I1 going from F to E, but now the actual current will flow from A to F. So the current value is 3 by 23 value of the current, but direction is from E to F. You indicated from F to E, then you proceeded, but you got negative, meaning actual current flows from E to F. Magnitude 3 by 23, decimal notation 0.13 ampere. This is the answer. So one method is over. Which method is over? Kirchhoff's rules method is over. Using Kirchhoff's rules method is over. We go to the next method. I given here negative symbol indicates that the actual current flows from E to F. Okay? Yeah. Then we go to the second method. What is that? Using combination of cells in parallel method. See here. The same circuit I have given. Now, this resistance you can take as the internal resistance for the cell. So even if it is given internal resistance of 6 volt cell is 3 ohm, you will show it like this. Always the internal resistance is shown to be in series with the cell. So this you can take as the internal resistance of this cell. For this cell, you know, these two are in series, 3 and 2. So you can put together as 5 ohm because they are in series here along with the cell. So you can say 5 ohm is in series with 9 volt. So 5 ohm you can take as the internal resistance of this battery, just for the application of the concept of combination of cells in parallel. Then this will be the external resistance 1 ohm. So you redraw the circuit, comes like this. See, this looks little simple. 2 and 3, so 5 ohm in series with 9 volt, right? Then 6 and 3, 6 volt and 3 ohm series. Then 1 ohm is the external resistance. Now you have to see the polarities. So left side for the 9 volt battery, left side is positive. For the 6 volt battery, right side is positive. I use the word left side and right side as you see in the circuit diagram. So just for convenience sake. Now we know how to find out the effective internal resistance and effective EMF, and you can redraw it in a simpler way, and we will know how to find the current through the external resistance. Okay, first to find the net resistance of the circuit excluding this 1 ohm, like we do it in the case of combination of parallel cells. Take as E1, E2, R2, R1. I have indicated no, just for writing the formula E1, E2, R1, R2. This is external resistance, capital R. Okay. Also I indicated diagrams as per this diagram here. I have translated it here. So which terminal or which end is F? The one which is connected to negative of the 6 volt battery. So this is F connected to the negative of the 6 volt battery. So this is F and this is E. Okay, right. Cells in parallel. You have to refer to this diagram. We know the formula 1 by R is equal to 1 by R1 plus 1 by R2. Apply it here. So effective internal resistance, though once again I repeat, though not given these are internal resistance in the question, but the approach will give you the correct answer. Even if you take it as internal resistance, it is not a very big harm. Okay, so I call this as net internal resistance, though not given in the question as internal resistance, but the approach will yield the correct result. So R is equal to 15 by 8 ohm. We know that V2 by R2. This also we know from the combination of parallel cells. This will help us to find out the net EMF. That means the EMF of a single battery which can replace the two given cells. So take this R to the right side. R we already know, so you can take this R to the right side. E1, R1, E2, R2 all we know. Right? E1 is 9, R1 is 5, E2 is 6, R2 is 3. Substitute. And R of course is 15 by 8. You can find the EMF value. See here, there is a negative symbol introduced. That's because here the polarity is changed. Here positive, but here this side it is negative. So because the polarities are changed, we have to put -6. And note that for the cell whose positive is on the left side, the EMF is +9. For the cell with the positive on the right side, the EMF is negative. That's how we have proceeded. Okay, simplify. -3 by 8 volt. Look at this negative symbol. So the single EMF is having a single cell is having an EMF 3 by 8 volt, but with a negative symbol. So accordingly we have to draw the equivalent diagram like this. Okay. See here, because we got -3 by 8, I have to put the negative polarity of the battery on the left side. That's how we have proceeded through all these steps. So 3 by 8 volt magnitude wise, but the negative polarity should come here. Negative polarity has come here, that's why we took as -6. We have to maintain it. Okay. So now you can easily find out what is the current through this 1 ohm resistance. Okay. So E is 3 by 8. Small r 15 by 8 we found. Capital R is 1 ohm. Substitute, simplify, 8 will cancel. You will get 3 by 23, which is nothing but 0.13 ampere. This time you are not getting negative symbol, because this current is to be flowing this way. Okay, I will indicate the current, because the current has to come from the positive to the polarity. So 3 by 23 ampere flowing this way, which is nothing but E to F. See here, E to F. So 3 by 23 ampere flowing from E to F. We got the same answer as we got by the first method. Okay. Next method is superposition theorem. Generally, the students may not have studied superposition theorem in 12th standard, but this will be useful. Superposition theorem. We will learn a new method. So, using the superposition theorem, how to find out the current through the 1 ohm resistance. So, we will now use superposition theorem and find the current through this 1 ohm resistance. Okay. So, how to do that? Of course, the application of superposition theorem has got its own restrictions, but in this case we can apply superposition theorem. The source of EMFs are these batteries and the elements are the resistances. We can apply superposition theorem. What does the superposition theorem say? See, we want to find the current through 1 ohm resistance. The current through 1 ohm resistance is the algebraic sum of the currents passing through it, assuming one cell is acting at a time. The other cell is simply inactive. That is superposition algebraic sum. So, algebraic sum of the currents passing through this 1 ohm resistance when each cell is acting singly in the absence of the other cell. So, first you will have to assume only one cell, this cell is acting, find the current. Then assume this cell is acting, find the current. That is, at one particular step you will have to assume only one cell is acting, the other cell is short circuited. The other cell is absent, but the path is there. Okay, so current will flow. So only one cell at a time, find the currents, find the algebraic sum of the currents. See here. Now I have removed the cell, but the path is there. This cell is there, acting now. I have to find the current through 1 ohm resistance. So how do you proceed? These two are in parallel. This parallel resistance is in series. Then you find out the current from the battery. That current will distribute here between the two parallel combination in the reciprocal ratio of resistances. So this 3 ohm and 1 ohm in parallel, as is obvious from the diagram. Therefore, the effective resistance of this 3 ohm and 1 ohm is 3 by 4 ohm. That is 1 plus 1 by 3, 4 by 3, reciprocal 3 by 4, or R1 R2 by R1 plus R2. That also we can use. So 3 by 4 ohm. Then this 3 by 4 ohm is in series with this. So 3 by 4 plus 5. So 23 by 4 ohm is the effective resistance. So find out the current drawn from the battery. The current from the battery 9 volt. What is the current drawn? Effective resistance being 23 by 4 ohm. So 36 by 23 ampere, because V by R effective, V is this 9 volt, R effective is 23 by 4. So 9 by 23 by 4, that will go to the numerator, that 4 will go to the numerator. You got 4 into 9, 36 by 23 ampere is the current from the 9 volt battery. 36 by 23 ampere. But this current, you know, when it comes like this, then it has to be divided between these two in the reciprocal ratio of resistances. That is, out of 4 parts, look at the resistance value. Out of the 4 parts, 3 parts of 36 by 23 ampere will go through this inverse ratio of resistances. Okay, so draw the equivalent circuit. (36 by 23 ampere current is coming. When it is come here, it has to be, part of it should go through the 1 ohm resistance, the remaining part should go to 3 ohm resistance. So out of 4 parts, 3 parts will go through the 1 ohm resistance. Out of 4 parts of what? 4 parts of this 36 by 23 ampere, the total current. That is, the total current should be divided in the reciprocal ratio of the resistance, 3 and 1 ohm. So out of 4 parts of this 36 by 23, 3 parts will go here, 1 part will go here. So So through 1 ohm resistance, now the current is 27 by 23 ampere when only this cell is acting. So through this 1 ohm, 27 by 23 ampere. I have called it as I1. Now what you should do, you assume this cell is acting, you remove this cell and complete this part and find out the current in the similar manner. Okay, I have given this circuit. Now 6 volt is considered, 9 volt not considered, but the path is complete. Okay, don't give any break in the circuit. Now these two are in parallel, that in series. Find the effective current, then distribution of current. 1 ohm and 5 ohm in parallel. So 5 by 6 ohm effective. This 5 by 6 ohm is in series with this 3 ohm. So 3 plus 5 by 6. 23 by 6 ohm is the effective resistance. So find out the current drawn from the battery. Which is 36 by 23 ampere. E by R effective. E is 6. R effective 26 by 23 by 6. That 6 will go to this numerator. So 6 into 6, 36, 23 here. 36 by 23 ampere is the current from the battery. I draw the equivalent circuit or the simplified circuit. Okay. This one we will prove. This one we will prove. Right. See here, current drawn from the battery 36 by 23 ampere is coming. So through this 3 ohm resistance also 36 by 23. But it has to be divided between these two. Again, out of 6 parts, 5 parts should go through this 1 ohm resistance. Because of the same argument we already mentioned. So 36 by 23 into 5 by 6 will go through this 1 ohm resistance. Okay, that 6 and 36, you know, that you can cancel. So 30 by 23 if you want. So this now flows from E to F. The current will go along this E to F. Okay. Earlier we got it from F to E. That was 27 by 23. Now this is 30 by 23. So algebraic sum. You can take this first because this is greater. No, you can just algebraic sum means 30 by 23 minus 27 by 23. So net current through 1 ohm resistance see here, easily you are getting 3 by 23 ampere, same answer, going from E to F. Because E to F greater current, F to E smaller current, so net current will go from E to F with the magnitude 3 by 23 ampere. Understood method? This method is called using superposition theorem. Superposition theorem. Superposition theorem. Understood this? Thank you.